Okay, Assalamualaikum warahmatullahi wabarakatuh and very good day. So for this video, I'm going to recall all the basic technique that we have in mathematics. So this part is not covered in our syllabus, but we are going to apply them frequently in our courses. Okay, so basically these are the things that I'm going to cover. So first one is direct proof, second one is proof by contradiction, third one proof by contrapositive, fourth is case word proof, the fifth one is counter example, and the last one and the most popular techniques that we use is proof by the induction. So I believe that you already familiar or you already meet with this kind of proving before, but what I'm going to do today is I'm going to give you just a brief introduction or brief recall and how you can understand the proof by using a logical thinking. Okay, so first one is proof by a direct method. So a proof by direct method, we just apply we have three steps, and the first one we are going to assume the statement is true, and we are going to derive logically from the assumption to get the final conclusion. And the last one, or last step, we are going to write the conclusion. Okay, so I would like to give the analogy for direct proof. So, for example, we have or we want to bake a cake. So here we are having the right ingredient. So that right ingredient is actually the true statement. And then we follow the step in the recipe, and which is in the direct proof is the logical deduction, and then you are getting a cake, which is a final conclusion. So this is just a direct way. So it means that for example in our analogy, we have the right ingredient with the following the step given by the recipe, and then after doing all the things you will get a cake. So it's just a direct case. Okay, so for example in mathematics, if you want to prove if n is an even integer, then n squared is also even integer, even number, then you can prove this one by using direct method. First of all, we are going to assume n to be even integer. Then n can be written as n equal to 2k here. So this is from our assumption, and from what we know based on our previous study, when n is even, then we can write n is equal to 2k. So our aim now is to prove n squared is also even. So what we are going to do today, what we are going to do is we are going to take square of this n. So square of this n is equivalently square of 2k. So with square of 2k, we are going to get 4k square, in which we can factor out 2 outside here, and we can see that this n square is actually multiple of 2. So means that n square is divisible by 2, means that it is even number. So it's just a direct way. So you start from the assumption. So we just do some process or some manipulation here, and then we get to the final answer, which is n squared is even for this particular example. Okay, so next one, proof by contradiction. So proof by contradiction is one of the popular method that we use in mathematics. So basically, to prove by contradiction, we are going to assume the opposite of what we are trying to prove. Okay, and show that this assumption will lead to a contradiction. So you are not directly go to the problem, but you assume the inverse. Then with that assumption, you show that there is some problem with the some problem or some contradiction with the assumption. Okay, so if you having problem to understand the proof by contradiction, I would suggest you try to understand this analogy first. Okay, so let us read together this one. Imagine that you are standing in front of a door. Okay, so you are standing in front of a door and you know that the door should be locked. Okay, so you just stand there and you know that the door should be locked, but you are not sure yet whether the door is locked or not, but you want to make sure the door is indeedly locked. So how you can prove this one? So therefore, instead of directly checking it, I mean the directly checking it, you have to show it is locked, right? So meaning that you need to look the mechanical system of lock is working there. So for example, you can x-ray the door and then you can look where is the mechanical system of the locking system. It's already turns on, right? That is a direct way. But that things on the step there, the x-ray and directly is going to be quite difficult and quite pricey, right? So therefore, we can use the proof by contradiction. So first one, we want to show that the door is locked, right? So we are going to assume the other way around. So what do you mean by assume the other way around? We assume the opposite. So in our case, if we assume the opposite, means that we are assuming the door is not locked, right? So if the door is not locked, means that the door can be opened or can be easily opened. So now, the second step is show the assumption lead to a contradiction. Okay, so now you are push the door and try to open it, but it doesn't open. In fact, it is firmly closed. So this lead you a contradiction. So when you try to open the door and it is not opening, so therefore this your assumption here, the door is not locked, is having a problem, means that it leads to a contradiction. So I repeat again, your assumption here, your early assumption, because you this on the first step you assume that the door is not locked, right? So when you try to open the door, it is firmly closed. So therefore your assumption lead to a contradiction. So this contradiction happen because of your assumption here. Your assumption door is not locked. So therefore you can conclude that the door must be locked. Okay, so try to understand the analogy and try to get the feeling of the contradiction there. Okay, so because we are going to use a lot of techniques contradiction in our proof. Okay, so next one is proof by contrapositive. So to prove by contrapositive, we have let's say that we are given the original statement if P then Q, and the contrapositive is that if not Q then not P. So basically these two statements, I mean the original statement and the contrapositive statement, they are equivalently same. Okay, so we can prove this statement if P then Q, or we also can prove if not Q then not P. Sometimes it is easier to prove in the by using contrapositive statement. So if we can show that if not Q then not P, then it is equivalent to if P then Q. Okay, so to understand the this technique, contrapositive technique, so I give you another analogy here: mother and her baby in the belly. Okay, so if the original statement saying like this, if the mother in the clinic, then the baby in the belly will be in the clinic. So I repeat, if the mother in the clinic, then the baby will be in the clinic. So of course here you can imagine that if the mother is in the clinic, then of course the baby inside the belly will be also in the clinic. Okay, so sorry, this one will be should be contrapositive statement, not the original statement. So the contrapositive statement is that if the baby is not in the clinic, then the mother is not in the clinic also, right? So it is not possible to have uh, the it is if the baby is not in the clinic, then of course the mother also will be not in the clinic also, right? Okay, so therefore the original statement and the contrapositive statement give you the same meaning. Okay, so next one, case work proof. So this case word proof is I think is very directly. You can understand this technique very clearly. So we just divide the statement into all possible cases, and we prove each of the individual cases one by one. If all the cases are checked, then the original statement is proven. Okay. So for this one, this thing I think no need for to have analogy because it's very direct. And then the next one is counter example. So counter example here, if we have a so to prove a universal statement, so we can provide a counter example. So here in this case, if we can find one example that does not satisfy the universal statement, then the statement itself is false. For example, I can say that if all the people inside this world are male, right? So of course the statement is wrong. So how to prove the statement is wrong? So I can just take one of your friend or one of your female friend, then that female is of course she is people, so therefore my universal statement there already wrong. Okay. So next one is proof by the induction. So let Pn be an accession involving an arbitrary n. So suppose that P1 is true, and if Pk is true, then Pk plus 1 is also true. Then if these two statements are true, Pn is true for any n inside the natural number. So this is a formal theorem proved by induction. So the other technique of proving, I didn't give any proving because it is just a logical thinking. But the proof by induction, we have one theorem here. So to prove this theorem, so the proving is also included in your textbook. You can refer to your textbook also. So to prove by induction here, first of all, we are going to assume one Roman and two Roman whole here. So we are going to use technique contradiction here. So we are going to suppose the other way around of this one. Okay, so we are going to suppose that there are some n inside the natural number, which is Pn here. So so means that Pn false. So I'm going to collect such number inside the set of S. So I'm going to call set of S n inside the natural number such that Pn is 4. Okay. So I collect all the Pn which is 4 inside the set of S, because here I suppose that there exists Pn which fall for some n inside the natural number. So now by well ordering theorem, so the last theorem in the last video, so by well ordering theorem, so we can find, because S here is subset of natural number, so we can find k which is more than 0, so more than 1, which is smallest element of S. Of course k here cannot be of course you can ask me why k must be more than 1. So k cannot be equal to 1 exactly, because we already have assumption P1 is true. Right, so k here is element of S. So whenever k is element of S, Pn must be 4. So therefore k cannot be equal to 1. So here that's why we can assume that k must be bigger than 1, which is the smallest element of S. So keep in your mind, element of S is whenever Pn is 4. So now we have k which is element of S. So therefore, when k is the smallest element of S, when we minus 1, so k minus 1 should not be inside the S anymore. So therefore, pk minus 1 is true. So I'm missing here the wording here. So therefore pk minus 1 must be true. So since pk minus 1 is true, so based on this one is we prove it, because k is the smallest element of S. So S is the false statement. So whenever we minus 1, so k minus 1 should be outside of S already, because k is the smallest element. So when we minus again, which is we get another smaller number than k, so it has to be outside of S. Okay, so here we prove that k minus 1 whenever it is outside of S, so means that the pk minus 1 is true. Okay, so since pk is minus 1 is true, by statement number 2 here, pk plus 1, so means that pk minus 1 plus 1 must be true statement. So imply that, so whenever pk is true, so means that k does not happen to be inside S. So this is a contradiction, because from the beginning here we assume that k is the smallest element of S, but at the end we come out with the k is not belong to S, which is a contradiction. So this contradiction happen because we assume that there exists some Pn which is fail for some n inside the natural number. So this assumption is indeed wrong. So therefore the truth one is that Pn is true for any n inside natural number. So this is a proof by induction. So that's why whenever we test, whenever we have a test for the first one, for the base one, and we test for the we assume for k, and we prove that for k plus 1 is also true, then we can imply it is true for any natural number. So that is a proof by induction. So I think that's all for this time. So thank you for watching.